So some exponential equations don't have the same base. So we can still deal with this, but unfortunately it's going to get a little bit messy. We can choose one of the two bases to work with, doesn't really matter which one, or we can just go straight to the common or natural log, because we're going to have to anyway. If we use a logarithm base 5, that will cancel out nicely over here, but over here we're going to get a mismatch of the base of the logarithm to the base of the exponential. So we're going to eventually have to turn to the change of base formula anyway. So again, whichever you are comfortable with. What we're going to try here is working with, just because it's already on the left side, we're going to work with the logarithm base 5. Now, I could have done this in the PowerPoint, but I think you're going to find as we go through it that this gets a little bit ugly. So again, I know this side has a exponentiation base 4, but if we're going to do a log base 5 on one side, we have to do the same operation on the other side. So fortunately, at least on the one side, the log base 5 and the exponentiation base 5 cancel each other out. On the other side, we're not so lucky. What we can do, however, is use the power property of logarithms to bring the x minus 7 down in front. Now, this is something that in the earlier videos when we were undoing exponentials with logarithms, I cautioned you about, because to bring an entire expression down in front means we have to make sure we put it in parentheses. That's actually very important in this case. Always important, yes, but in this case in particular, it would make the problem very, very different if we forgot to do that. Now, part of the reason that I chose to use a logarithm that did match at least one of the bases is because it keeps this wrapped up into a smaller statement. Eventually, we're going to have to turn to the change of base formula, but for the moment, that's probably the best form for it, because this is going to get a little bit messy over here. Now, one of the important things to remember is that, as weird as that looks, this is actually a constant, no different than a 7 or a 1 or a 3. This is a constant. So, like any linear equation, if we want to solve for x, we have to start by getting all the x's on the same side. But before we can even do that, we need this side to not have those parentheses around it. We can't just divide both sides by log base 5 of 4, because then we'd have to distribute it over here. So it's going to have to be distributed one way or the other. We might as well do it on this side, and you can see how this is going to start to get a bit ugly. So we're going to have x times log base 5 of 4 minus 7 times log base 5 of 4. So again, not pretty. This is a constant, and so is this. So what we have is our x terms on opposite sides, we need to get them together, and our constants on opposite sides, we need to get them together as well. So we can subtract the x log times log base 5 of 4 from both sides. That's going to give us 3x minus x times log base 5 of 4. Now we also have to get the constants together, since we got the x's on the left side, the constants on the right side. So we'll subtract 1 and subtract 1. Now be careful. We can't do negative 7 minus 1, because it's not negative 7. It's negative 7 times the log base 5 of 4. So much like over here, we had to leave these two things separate, at least for the moment. We're going to have to do that with these two as well. That is the best we can do with it at the moment. Now, that's unfortunately as good as that side's ever going to get until we go to a calculator, which we're not going to just yet. We're going to focus on this side. Now, this is an ugly constant, but it is still a constant. If we had had, say, 3x minus 2x, we would just subtract the coefficients, 3 minus 2, and basically factor out the x. Well, we can do that here. We can factor out the x, and leaves us with 3 minus log base 5 of 4. Not an expression not entirely unlike this. And we're almost there. The last step to get x by itself is to divide both sides by this expression. So when all is said and done, we're going to have x is equal to negative 7 log base 5 of 4 minus 1 over 3 minus log base 5 of 4. And again, it's not pretty, but that's the best we're going to get. This would be the exact form of the answer. If we wanted a numerical form that could be rounded to a certain number of decimal places, we can use the change of base formula to evaluate this. It's going to get big and messy, but can it be done? Yes, it can. So I would like to point out, you're not going to see many equations such as this, and to be honest, I'm not mean enough to give you a question like that on a test. That's a little bit excessive. You don't see things like that quite that often. But there are one or two of them in the homework problems. We should be prepared to deal with them when they occur. But I don't need to give you the hardest possible question on the test, certainly. But yeah, it's not pretty, but that's how you can do it. So, again, we could have used the common or natural log up here. It would have gotten disgusting because we would have had, instead of one side times a logarithm like that, we would have had a logarithm on both sides, and it would have gotten really kind of disgusting to write. More so than it already is right now, but regardless, at the end we would have to turn to the change of base formula in order to actually evaluate this, and if we wanted a decimal form. No, not pretty, but there it is.